Hello everyone, today we are going to present our Reaction Engineering 2 project, and the topic of our project is hydrodesulfurization of crude oil fraction. Hello, I'm Chua Chong Ling from Group 3.
Hi everyone, I'm Wong Yi.
Hello everyone, I'm Sylvia Liu Jiayi.
Hello there, I'm Lim Le Qi.
Hi everyone, I'm Helmi.
First, let us talk about what is hydrodesulfurization process. Hydrodesulfurization is a catalytic chemical process widely used to remove sulfur from natural gas and refined petroleum products. For example, gasoline, jet fuel, kerosene, diesel, and fuel oil. Thus, the objective of application of hydrodesulfurization process is used to remove sulfur and create a product that is ultra-low sulfur. The hydrogen sulfide gas is then converted into sulfur and sulfuric acid. In this project, we are going to present how diesel is produced through hydrodesulfurization process.
In this session, NiMOW, COMO, and NiMO type catalyst will be discussed. Based on the figure, FHUDS exhibits the lowest activity in performing HDS, while FHUDS6 possesses the highest activity. In this project, we will be performing hydrogenation route, and the suitable catalysts are FHUDS3, 2, and 6. Since hydrogenation approach will be hindered at high rate average back temperature due to stable hindrance, FHUDS6 with higher Bronsted acid content will be selected, as it can improve the alkyl transfer reactivity during reaction. NiMO type catalyst is suitable for feedstock with higher amount of nitrogen and aromatic hydrocarbon contents, while COMO type catalyst works well for feedstock that contrasts with NiMO feedstock. Since 460 MTBT is mostly presented in feedstock with higher concentration of aromatics, NiMO type catalyst is primarily considered. The figure here demonstrates that the selectivity of 460 MTBT by NiMO catalyst is higher, as less sulfur is distributed in the cell after HDS. In conclusion, NiMO type catalyst FHUDS6 will be chosen as the optimal catalyst for our reactor design.
To determine the rate limiting step, the following steps are conducted. Getting kinetic data from article, make assumption on rate limiting step, whether it's adsorption, surface reaction, or desorption limited. Derive the rate law equation, plot a graph based on the derived rate law equation. Compare the graph plotted to the actual graph obtained from article. If the graphs are similar, the assumption made is correct. Else, the assumption is changed and the steps are repeated until the experimented data fits the model. The hydrodesulfurization of diesel process is to remove sulfur compound in diesel. The chemical equation for this reaction is as shown in the current slide. 46-DMDBT is adsorbed on surface and reacts with hydrogen in gas phase to produce C14H12 compound and hydrogen sulfide in gas phase. Assuming adsorption is rate limiting, the equation for adsorption is derived based on the assumption that it is non-dissociative. Then, assuming irreversible reaction, the equation for surface reaction to form adsorbed C14H12 and hydrogen sulfide is derived. Next, the rate equation for desorption is derived for C14H12 compound. H2S form is released in the gas phase, hence there is no desorption for H2S. As adsorption is assumed to be rate limiting, the rate of adsorption is equal to the rate of reaction. For adsorption limited reactions, the value of Ka is very small, hence it can be considered that Rs over Ks and Rd over Kd equals to 0. The rate law equation is then further simplified. The next part is the elimination of the concentration of vacant sites with Cv. Total sites is equal to vacant sites plus occupied sites. The equation is rearranged. By substituting Cv to the simplified rate law equation, the final rate law equation is obtained. For this section, a graph is plotted based on the derived rate law equation. From the rate equation, rate is proportional to the concentration of A. Therefore, a linear graph will be obtained. By comparing the plotted graph with experimental graph, the assumption made is true. Hence, it can be concluded that adsorption is the rate limiting step.
The reactor used for the hydrodesulfurization of diesel is the trickle bed reactor. It has an inner tube with diameter 2 cm and a length of 65 cm. There are three parts in this reactor, which are shown in the figure here. We start with the lactic fraction HDS zone. The feed inlet has 0.706% of sulfur. It operates at 360 degrees Celsius and 2.9 MPa. The total reaction time is 20 minutes, where sulfur is reduced to 0.092%. The light fraction product is around 43%, and the final product temperature is less than 300 degrees Celsius. Also, it has a relative fluorescent intensity of 25.7. In the HDS zone for the first stage heavier fraction, it is used to desulfurize unreactive sulfur compounds at a temperature of 360 degrees Celsius and pressure of 2.9 MPa. The reaction time for this stage is 45 minutes, where the sulfur level will be reduced to 0.035%. The RFI of the product at the end is 30.2. The third stage operates at 300 degrees Celsius and 2.9 MPa. The total reaction time for this stage is 10 minutes, where sulfur will be reduced to 0.016%, and the product desulfurized is 37%. The final temperature will be 300 degrees Celsius and RFI of 5.0.
First thing first, on our topic of hydrodesulfications, the catalyst deactivation involved in this topic could be the coking, since the carbon that form at the interface of the active metal, it also blocks the active sites of the catalyst itself. So in order to regenerate regenerate the catalyst, we have proposed by contacting the steam with the non-diluting solvent at the temperature of 600 degrees Celsius. So we have proposed our reactor that should be the packed bed reactor. First thing first, for the reactor design, these are the assumptions that have been made. And from the genus itself, for the operating properties, these are the information that we obtain. In our reaction, basically is to remove the sulfur compound in 4,6-DMDBT, noted as A, to become the kerosene, which is noted as C. First of all, we start with the mole balance itself. We can derive the weight of the catalyst, W equal to Fa0 integrate dx over negative Ra. So for the rate law itself, we assume that it is the pseudo first order reactions, and we proceed with the expansion factor, which is equal to 0. So furthermore, we proceed with our energy balance. So we have to find another equation in terms of T, and after that we substitute it into the PBR balance equation. So to calculate the weight of catalyst in PBR reactor, we have used the Microsoft Excel to plot the data. From the right side, you can see the weight of the catalyst can be calculated from the area under the curve. At the last part, we use the Simpson rule in order to calculate the weight of the catalyst, which is equal to 80.64 kg. And after that, we use the bulk density that we found, which is 0.84, and we able to calculate the volume of PBR, which is equal to 0.96 meter cubic.
In summary, the selection of suitable catalysts used among FHUDS-5 and FHUDS-6 catalysts is based on the feed condition. Then, the rate limiting is determined by using initial assumption of letting absorption as rate limiting, since the graph obtained in figure 3.2 is a linear graph. Thus, we can conclude that the absorption is rate limiting factor. Next, the basis of reactor is determined by doing some research on the column of hydrodesulfurization. The last, in reactor selection, PBR are chosen as our reactor column, and few assumptions are made in reactor selection and reactor design. Therefore, by following the step in Chapter 3 and Levenspiel plot, we are able to get the data during the reaction. This is all for us. Thank you.